Hi there, everyone. We are continuing our discussion of ANOVA techniques. ANOVA, of course, being short for analysis of variance, which, weird as it is, the naming convention has nothing to do with comparing variances with one another and everything to do with comparing different population means or population averages to one another. So this is a technique that allows us to look at multiple populations or multiple treatments at the same time and determine whether they differ from one another on average. We looked at the basic methodology in our previous class, but kind of ended up in this space where we could reject the null hypothesis of no difference and therefore conclude that there are differences, but not know which groups or which populations differ from one another in a statistically meaningful way. So digging in today, the multiple comparisons in ANOVA, we will be looking at ways of comparing these populations to one another after performing the ANOVA test to then determine in a post-hoc manner which ones have evidence of differing significantly. Right, so we're picking up today assuming that we've tested our ANOVA null hypothesis, that all the populations have equal means, but we have rejected that null hypothesis. If H0 is not rejected, then the data supports that all the groups or all the populations have equal means. But if we reject the null hypothesis, where this leaves us is with the knowledge that some of our populations, perhaps all, but perhaps just some, have means that differ from one another. But just rejecting the null hypothesis does not tell us where those differences are. And so we want to dig a little deeper to now find a way of establishing which populations differ and which ones do not differ from one another. And in a broad sense, the collection of procedures that allow us to do this are known as multiple comparison procedures. So these are methods where we can take all the group means and figure out which ones differ from one another. Now, what multiple comparison procedures in general have in common is that they are based on the idea of constructing multiple confidence intervals. So the central idea is that you're going to calculate confidence intervals for each pairwise difference. So in some sense, this is almost reducing the problem to repeatedly doing two sample comparisons, because the mu I minus mu j just means we want to know what the difference is between two population means, except in multiple comparisons, we want to do this for all indices I and j with I less than j. In other words, if I start writing that out specifically, what we would want is confidence intervals for mu1 minus mu2, mu1 minus mu3, mu1 minus mu4, however many groups you have. We would not do mu2 minus mu1 because that information is already contained in the interval for mu1 minus mu2. So we'd pick up mu2 minus mu3, mu2 minus mu4, and keep going with all possible pairwise confidence intervals. So this is not how we're going to eventually implement it, but multiple comparison procedures are based on the idea of what if we could construct all of these pairwise confidence intervals? And let's just make it very concrete with a specific example. Say we know that we have 3 different treatment groups, and we want to compare the treatment means to one another. In this instance, a multiple comparison procedure implemented directly through confidence intervals would construct a confidence interval for what I will call delta 1, 2, the difference between the first two treatment means, delta 2, 3, the difference between the second and third treatment means, and delta 1, 3, the difference between the first and third treatment means. But the number of confidence intervals grows with I. So if we only have 3 groups, we have to construct 3 confidence intervals. If we were doing this generically for I different groups, we would have to construct I times I minus 1 over 2 confidence intervals. And if you take a close look at that, that's quadratic in the number of groups. So the number of potential confidence intervals grows faster than the number of groups. Now, what can we learn from these confidence intervals if we were to construct them? Well, if we looked at any confidence interval, and that interval includes 0, then the specific pair of treatment means that refers to would suggest to us that those treatment means do not differ from one another. And on the other hand, if a confidence interval does not include 0, well, 0 not being in the interval tells us that we are seeing statistical evidence of a difference between those treatment means. So that's how we would interpret these at the confidence interval level. Now, there are different approaches to constructing these confidence intervals. But the method we're going to focus on today is known as Tukey's procedure, or sometimes just called the T method. Now, John Tukey, one of the early mathematical statisticians, one of his big claims to fame was that during World War II, it is believed that he helped to invent the U-2 spy plane. He was also one of the first founders of an academic discipline of statistics. Like prior to Tukey, it was always just kind of one office hidden away in a math department. And Tukey brought more prominence to statistics and in fact resulted in a lot of schools creating an expanded role for statistics or even forming their own statistics departments. Now, Tukey's contribution here, as relevant to multiple comparison procedures, has to do with his defining of what is known as a studentized range distribution. Now, this is a distribution with, again, 2 degrees of freedom quantities, enumerator degrees of freedom, which we'll denote by M, and a denominator degrees of freedom, which we will denote by mu. And random variables or quantities from this distribution generically go by the letter Q. So if you see a Q with 3 subscripts, the first of those being an alpha and then 2 degrees of freedom quantities, that's telling you that you are looking at a distribution Q, or a studentized range distribution, with M and mu degrees of freedom, and you are trying to find the value where, if you're looking at the distribution, the tail area associated with that specific value is alpha. So it's consistent with notation we've used throughout. The alpha in the subscript tells us what the area to the right is. The studentized range distribution is a strictly positive distribution, like the chi-square, like the F distribution. And in our live session on Zoom, we'll take a closer look at this table. This is one of the few instances where, regardless of which calculator you're using, your calculator is not going to help you with this distribution. So we have to use the table that's in the book. But we'll spend some time on that during our live session. Now, if we think of the group means as random variables, so we have I different groups, and each group has an average of j different random observations, then the ith group average is a random variable that behaves like the average of j independent and identically distributed random variables. We're still following the ANOVA convention of assuming normal distributions for all our observations, and we're also assuming common variances for the different populations or the different treatments. Then, with probability 1 minus alpha, the following statement is true. If we look at the difference mu I minus mu j, the true value of the difference will be contained in the random interval defined by the ith group average minus the jth group average, plus or minus a critical value chosen from the studentized range distribution, let me just get back to the correct spot here. I apologize. Okay, let me start that sentence over. If we look at the difference, mu I minus mu j, so the difference between the two groups, their treatment means or their population means, that true difference will be contained in the random interval defined by the difference of the random group means plus or minus this Q quantity taken from the studentized range distribution multiplied by the square root of the mean square error over the number of observations per group. And so this looks a little bit like the confidence interval for the difference of two means that we previously constructed, except the t value has now been replaced with the q value, and we have the mean square error in here. But what makes this quantity unique is that this holds for all I and j, as long as I is less than j. That's just a technical condition, which ensures that we're not doubling up on confidence intervals. We're not constructing one for mu1 minus mu2 and also one for mu2 minus mu1. And I and j range from 1 to big I. And again, this means that this probability 1 minus alpha does not apply just to an individual confidence interval, but holds simultaneously for all these confidence intervals that can be constructed. So their joint coverage is 1 minus alpha. If you think back a little bit to when we were wrapping up hypothesis testing in chapter 8 and talking about multiple testing, it's equivalent to the difference of an individual test type 1 error and an overall test type 1 error. So what this interval is ensuring is that our overall type 1 error rate is 1 minus alpha, as opposed to each individual confidence interval having a level 1 minus alpha. So practically, the way you would implement this is if you have your observed group means, x1 dot bar through xi dot bar, and you have your mean square error calculated, then you're going to construct confidence intervals, x bar I dot minus X bar J dot plus or minus a Q value taken from that studentized range distribution multiplied by the square root of MSE over J. And you will do this for all pairs I and J such that you construct all possible confidence intervals. And then their joint coverage will be 1 minus alpha. Now, going through this, it's kind of a tedious procedure if you're going to construct all these confidence intervals, and it's not the most practical approach to the solution. So what we end up doing with the Tukey method is finding a little bit of a shortcut. So the way the shortcut works is you first make sure that you specified your overall type 1 error rate alpha, and then using that quantity, you calculate the number W. That's defined as the Q value taken from the studentized range distribution multiplied by square root of the mean square error over J. So it's the step length in the confidence interval formula on the previous slide. Now you calculate this quantity W. Then you run through the following steps. You take your sample means and you list them in increasing order. And when you look at any two sample means in increasing order, if you notice that there are sample means that differ by less than this quantity W, you underline those. Values that are jointly underlined are deemed to not differ from one another significantly because they're within the step size W from one another. But any pairs that are not underlined are deemed to be significantly different because the reason they are not underlined is they are far enough apart. In other words, they're more than the step size W apart in either direction that we can conclude there's evidence of a statistical difference. So I know at the moment this may sound very abstract, but we will do a couple of very practical examples of this during our live Zoom session to see how this is implemented in practice. I think ultimately what you want to keep in mind with multiple testing is the following. Multiple testing, or doing this multiple comparison procedure, allows us to control the overall type 1 error rate rather than the individual error rate. And the reason Tukey's method exists rather than just working with the t-distribution is because we don't have the independence assumption we need if we just wanted to construct multiple intervals. Why not? Why do we not have independence? Because there are, if we were constructing confidence intervals, there are multiple confidence intervals that include the same group average. So if you look at the ith group, little I, then it's going to be compared to big I minus 1 other groups. So it will show up in a whole bunch of these confidence intervals. And also, all of them are based on the same mean square error quantity. So they all share the same MSE quantity. Many of them share the same group averages, and so independence cannot be assumed. We can't make an adjustment to the alpha level just assuming independence. And so that is why the studentized range distribution attributable to Tukey is so important. So we will really dig into this tomorrow. But with this, we are wrapping up chapter 10, and next week we will look at some content in chapter 12.